Okay, now I'm coming to the design of the gravel trap. Okay, and basically the gravel trap is required to flush out bed sediments that enter the approach canal. Okay, uh, and it is designed to collect maximum 12 hours of gravel deposit. So the key parts of the gravel trap is you have to decide on the size of the trap required. Uh, the basically the length and of course the width of the trap, because we need to whatever small gravels and sediments, bed sediments that enter the intake will flow here, and in this length the critical velocity, the velocity is controlled. So the sediment particles size will basically deposit on the bottom section, and this is flushed out once in a while when this the bottom of the gravel trap is full. Then we open the gates. This is the gate here, and it is flushed back to the river. Okay, so and then after the gravel trap is the basically the canal that will start and deliver water to the powerhouse, the forebay first, then to the powerhouse. Okay. Now, what are the critical factors that we have to consider when you design the gravel trap? Okay. One parameter that needs to be decided is the critical velocity. And this critical velocity is to transfer the gravel. The critical velocity is calculated using a very simple formula called critical velocity should be equal to a square root of d. And for particle size of more than 1 millimeter. So what it does is it tries to settle, trap all particles that is more than 1 millimeter in the gravel trap. So basically the empirical coefficient is equal to A is equal to 44 for particle size, and D is the particle size to be transported by the flow in millimeters. So what is the particle that you want to transport to in this flow is given, is decided, and this is based on the based on this formula. And the length of this of the gravel trap is basically again decided using this formula, which is equal to T set times V, and T set is H over W, which is length of the settling trap in meters. T set is the settling time of particle, and H is the depth of flow in meter, and W is the settling velocity in meter per second. So based on that, we decide on the length of this gravel trap, and the flushing velocity is the is calculated again using the formula called phi times root under 2gh, and the coefficient for phi, velocity coefficient, is 0.6 to 0.8, and g is the acceleration due to gravity, and this is the differential head. The differential head is between the upstream head and the downstream head. And so this is the flushing velocity, and the flushing time is basically the volume of gravel water mix. What is the volume of the gravel water mix we in cubic meters second divided by the flushing discharge at the gallery. So this flushing discharge is also decided based on the size of the of the opening of the gravel outlet, trap outlet. So and basically this is the, the basic conceptual design of the gravel trap. And this gravel trap is basically is collected so for not more than 12 hours of deposit. So normally during the wet season, when the sediment load is high, the the operation of the gravel trap will be more frequent, flushing. But during the dry season, the requirement will be less. So this is, we will do some exercises during the our next lecture sessions in probably early December and maybe in January. I have to check the schedule for these exercises. Okay, so I mean, just to give you an idea of what a gravel trap design is, this is the consider. I will now briefly go straight to settling basin also, because the philosophy of the settling basin and the gravel trap is more or less same. Gravel trap is basically trapping a larger particles of sediments, whereas settling basin will trap smaller. Okay, and basically settling basin gravel traps are basically trapping more or less the bed load. Okay, what it moves on in the just above the bed level of the river. But, but the settling basin is basically trying to trap remove the suspended sediments, no, from entering the power plant. And this suspended sediment can be from as small as 0.002 millimeter, which is considered silt, and from and as large as 2 millimeter diameter, which is considered sand. So any material within this range is settled in the settling basin and then flushed back to the river. It doesn't, because this size of suspended sediment, if it enters the turbines, as I showed yesterday, the turbine runners will be damaged and the efficiency of the turbine will be reduced, which will mean there will be a loss of revenue, because loss of generation means loss of revenue, which will have an impact on the economics of the hydropower project. Okay, and the basic principle of a settling basin is it will reduce the velocity in the area, so that by increasing the cross-sectional area, so that because when the velocity increases, the particles of this size, the sediments of this size will fall, will not get transported, but it will come to the bottom. Then based on the bottom, based on the sediment deposits, then that is flushed separately. So the size of the basin will depend on the rate, how much of discharge we are using, size of the sediment, and the water quality required at the outlet. Okay, this is just an example of a 60 megawatt project in Nepal, where the picture is given for thing. But in our case, we are talking of smaller size mini hydro projects, and the size of these settling basins will be smaller than what you see on the picture here. And the basic design concepts, I will not go into very the detail of that so much, but I just want to give you an idea of what the design. When you design a settling basin, what you do is you basically find what is the fall velocity. Okay, so this fall velocity of the sediment. So what you have here is this is the canal. Then you have a settling basin, which is a little bit wider. Okay, so here, and velocity in the settling basin is different because of the larger cross-section area. When the water flows in the settling basin, the normal velocity decreases. And when the normal velocity decreases, these larger sediments from 0.002 millimeter to 2 millimeter size sediments basically fall on the bed of this settling basin. Okay, so we have to now decide what is the fall velocity, how long it will take for a sediment that enters here, let's say size 2 millimeter, it will slowly fall below in this. Let me just get the spotlight. Okay, what it happens, the sediment that is transferred here is basically, it falls here, and we call this a fall velocity. How long it will take for that sediment because of the velocity to fall here. And it depends on several factors. Of course, on the size of the sediment itself, the shape of the sediment, the density of the sediment, and viscosity and density of fluid. So if it is a viscous fluid, then it will be a different fall velocity. If it is, so it depends on the in these factor and the density. How density means, if it is heavy, no, density is weight divided by volume. Okay, so mass divided by volume is density. So if you have a dense sediment, then the fall velocity will be lower, and it will fall here very fast, higher and fall very fast. So this is, and this fall velocity, there are, you can find charts, design charts, where you can get this fall velocity for different sediment size particles. Okay, and the key design parameters is, what is the surface area required, what is the limiting flow velocity, and what is the length, breadth, and the depth of the settling basin. And the sediment depth in the basin is H, is how much of sediment that you will do, you will settle here. And this sediment is, again, like in the gravel trap, it is flushed back to the river. So this is basically a very simple settling basin conceptual design. During the exercise, I have some Excel sheets programs which will help you define these LBD factors for different flow rates, for different sediment sizes, and this we will practice later. Okay, Carlos, is there any question, specific question on gravel traps and settling basin?
Thank you, Jesus. Alguma pergunta para a matéria que foi colocada até agora? Alguma pergunta? No, Divas, thank you. You can proceed.
Okay. Yeah, thank you. Yeah, sorry, maybe if I'm going a little bit fast, let me know. But anyway, now I will come to other civil component, because I want to finish in this session all the civil parts. So I come now to the tunnels. Okay. For mini hydro, as I mentioned earlier, we don't really have projects which will have tunnels, because tunnels are expensive. Okay, because it is underground structure. But for small and medium and large hydros, and especially given the topography, tunnels can be an economic, cost-effective option to transfer water from the intake to the powerhouse. Okay? So tunnels are basically underground openings, and you basically drill using different methods, blast and drill. Nowadays, you have tunnel boring machines, but these are a little bit expensive. Different construction methodologies are available for tunnels. Okay? Now, so it can be pressure tunnels and non-pressure. By pressure tunnels, what it means is it's like a pipe flow. It's in under pressure, and the whole tunnel, the water fills the whole tunnel, and there is a potential energy still preserved in the tunnel. Okay, so now again, at the end of the day, apart from the cost, I mean the different size of the tunnel, what is important is the loss of head in the tunnel. When you transfer water through the tunnel, there are frictional loss. Okay, very simple technique to calculate the frictional loss is given by the famous Manning's formula, which is basically from the Manning's end. The formula is V square n square L divided by R to the power 4 by 3. N is the Manning's roughness coefficient. Okay, so I think we will also discuss the Manning's formula later. So we use this formula. So depending on the length, depending on the roughness coefficient, and depending on the hydraulic radius, the hydraulic radius is the size, then you get the head loss. And also we have to be careful when you do the tunnel, you have to consider the trash track losses like we did for the intake, the entrance losses, the transition losses, the bend, gate, and exit losses. Okay, so now when you decide on the size of the tunnel, because the larger size tunnels means the head loss is less, but the smaller size tunnel means the head loss is high. And tunnels are basically, more efficient is around the circular tunnel, but now we have what you call a horseshoe tunnels. So these are based on main construction methods, and the minimum size for manual construction is 2.54 meter diameter, because for workability, for people to enter and drill and blast, you need a minimum of a 2.5 meter diameter tunnels. But nowadays you have tunnels that are drilled using tunnel boring machines, okay, which can, I think, drill even smaller tunnels. Okay, now this is basically the principles of tunnel. But now the main important thing in tunnel design is what is the optimal tunnel size, basically the diameter. Now the question becomes, when the diameter increases, okay, this is the straight line here, the incremental cost, okay, of the tunnel increases with the diameter from 1, 2, 3, 4. Once you increases, it increases like this. But the revenue loss, okay, when the tunnel is 2 meter, diameter is 2 meter, the revenue loss is something like this is just an example, 3 million US dollar. And this is basically the revenue loss. The total cost is calculated based on this frictional loss and these head loss in the tunnel. Due to head loss, energy generation decreases, and any decrease in energy means you have decrease in revenue. So once you start increasing the tunnel diameter, the head loss also decreases and the loss of revenue also decreases. So if you have 4 or 5, there is almost practically very little head losses, so you will not lose any money. Okay, but now the question is, we have to find, because once you have larger diameter tunnels also mean the cost increases. So basically you have a curve, a total cost curve of cost minus the revenue loss, okay, revenue. So you get basically an optimal, you get a inverted U curve, okay. So the best total cost is somewhere with the minimum total cost in this case is around 3 meter, 3 point something meter. So the tunnel diameter we select is 3 point something meter. If you select 4 meter, 5 meter, the cost will increase. The savings, the benefit you get from reduced generation, from reduced revenue does not does not balance the additional cost you have for larger size diameter. So basically, when you design a tunnel, you calculate the cost, the diameter, and everything. Then you calculate the head loss in the tunnel, and from this head loss, you calculate the revenue that is lost because of the head loss. And based on the total cost, the cost of the tunnel minus the revenue loss, uh, you get the total cost of the tunnel, which then you find the minimum total cost of the tunnel, which is in this case is coming to 3 point something meter. So this is the basic principle for tunneling. I wanted to introduce you to this because it is an important consideration if you are doing a tunnel a project with a tunnel design. Okay. Now I will maybe go to the, if there is any question, I can address this later, but I will just now go to basically some principles of pipe flow and canal design. Okay. Now, basically, what I want to, because this pipe flow concept is important for penstock design also. So I want to basically explain what is the hydraulic of pipe flow. And when you do a pipe flow, today I'm being a little theoretical. Please tell me if it is getting a little difficult to understand. But I think it is important for you to understand these principles of fluid mechanics, which are hydraulics, which are important for design of structures for hydropower projects. There is a very famous equation called Bernoulli's equation. And Bernoulli equation is basically, it gives you the total energy of a flowing water, of a water, flowing water. If it is stable, it's just it's fixed water with that is not flowing, then it just has, as I mentioned, a potential energy, because if you drop that water, then you have this potential energy. But when you have a flowing water, the total energy is basically given by the total energy, and we basically define this energy by the head, okay, by the elevation difference from a datum. So there is a pipe, and water is flowing through this pipe. In the beginning, the water is flowing in a velocity of v1. At the outlet, it is at another point, it is flowing with a velocity of v2. Okay. Now, the total energy is equivalent to, because is the potential, is the elevation, head elevation. So from the datum, what is the head elevation? So Z1 is the elevation head. And the other is the pressure head. There is, because this water or fluid is flowing at a basically there's a pressure of this water flowing in this tube. So this pressure head is basically the P1 divided by gamma. Okay, this one is P1 divided by gamma, and gamma is the specific weight of water. And then there is this, what is known as the velocity head, which is given by E square by 2Z. So total, this is at this location. At another point downstream at Z2, the total energy is equal to Z2 plus P2 over gamma plus V2 square over TZ, and the energy line, the energy line consists of Z1 P by gamma, the potential energy, plus the velocity energy. Now, this energy gradient line is slightly decreasing here because there is a energy lost due to friction of water against the pipe wall and the internal friction of the flow. So the total energy here and the total energy here is there is a loss of energy. And this loss, the total energy here, is given by HF. So this equation of, because the energy cannot be conserved due to the principle of conservation of energy, the total energy here and the total energy here has to be equal. So Z1 P1 over gamma plus V1 square over 2G is equal to Z2 plus P2 over gamma plus V2 square over 2G plus the frictional loss, the total energy. So what has happened is the energy from here has been, part of that energy which is lost is converted into, is lost due to friction. There's the, so it has been converted into friction, and it could be heat and other factors. So this is the basic principle of a pipe flow. So whenever you calculate any the flow through a pipe, we use this principle. Okay, but in the case of canals, okay, this is the pipe flow. So we put Y2 as the isometric head, is the pressure head over here, Y2, and we P over gamma is considered as Y1. This is Z1, and this is the velocity head. This is in the case of pipe flow. In the case of uh, open channel flow, the difference is the water surface itself is the hydraulic gradient line, because suppose the pressure here in the pressure here is atmospheric pressure, which is 0. The pressure on the surface is atmospheric pressure, which is 0. Okay, so basically in open channel, hello Carlos, any question? Okay, in open channels, in canal, yeah, in open channels and canals, the pressure at the surface of the water is 0. So, but in a pipe, there is pressure. So there is a, what is known as the piezometric hydraulic pressure here in the inside the pipe. Whereas in the channel, it's basically the water surface is the hydraulic head. And this is the energy line, which is the total water surface and the velocity head, plus HF is the friction losses when the water travels from this point to the other. Okay, so this is the difference between a pipe flow and an open channel flow, and this is very important when you design a pipe or a canal. So, so I will just now introduce you to some of the basic design properties for a pipe, for a canal and a pipe later. Okay, in the case of canals, the canals used for hydropower projects like mini hydro projects, in the Majao hydropower project also there is a canal. So and they I think have a line canal. Okay, so line canal it can be a rectangular canal like this or a trapezoidal canal like this. And unlined canals will also be normally trapezoidal. Now, the only difference between line canal and unlined canal will be that in the line canal, the side slope can be little bit steep, but in the unlined canal, you have to maintain a certain slight slope. Otherwise, there will be erosion. So this is the difference. And of course, the cost of the line canals will be more than the unlined canals. But the line canals can also, the cross section will be smaller because the acceptable velocity can be higher than the unlined canals. So this is basically the typical sections. Now you have to now basically decide what is the most efficient channel section, the canal section. And this is basically again using the Manning's equation. And when you say the most efficient section, what we mean is a channel which can pass the maximum discharge for a given flow area and roughness coefficient and slope. For given n, the roughness coefficient and the slope, the Q is maximum when the weighted perimeter is minimum, because you see uh, the the hydraulic radius and the is basically is converted into area and perimeter. So basically you see Q is inversely proportional to the weighted perimeter of the section. So basically what you are trying to see is you want to find a cross section which will have the same, will pass the Q when with the minimum sort of uh, section of the canal that is wet, where the water meets the canal. And so if you do you can do an optimization exercise here, and basically for a rectangular canal, the most efficient section will be width will be 2 times the depth. For triangular side slope, the side slope should be 45 degrees. For trapezoidal, this is the formula we used. So we find the slope based on the depth and the base width of the project. So we have to find the most efficient section for different. This most efficient section means what is the ratio of T and H. So for rectangular, the width T should be 2 times the depth of water. Then that will be the most efficient section according to this most efficient section formula. Okay, and the Manning's end, the friction losses, basically Manning's end has for earthen channel, straight section, clean, it is 0.022. For straight with grass, it's 0.03. The more rough it is, the higher is the roughness coefficient. So for brickwork, for natural bed, it's 0.024 to 0.05. And this is based on empirical from studies from different areas and rivers. Okay, so basically the basic criteria we use to design the canal is for unlined canal, the velocity should be between 0.9 to 1.8 meter per second. Freeboard should be minimum 0.3 meter plus 1/10 of the full supply depth. And if you have a curve, or if the alignment is a curve, the curve ratio to width should be of the canal should be more than 3. And basically in a rectangular canal, B times H is the area. So these are the different hydraulic depth and calculations, everything given. And we use basically the Manning's N to A 1 upon N area times R square, R2 by 3, and the slope of the this water surface half to calculate the Q and to get the dimension, the width, the slope, the height of the canals. So this is basically the canal design. And we will, as I mentioned, we will do some exercise during our course of this training. So since I want to use, I think we have around 10 or something minutes more, I would like to finish this fast so that in the next session, I can start in a new topic, the electromechanical equivalent. But civil works, I want to finish before we break. So if you don't mind, I would just like to go ahead. And the third, and the other part is the penstocks. The penstock are from the pipes, pressure pipes, which goes to, which from the forebay, we take the water to the house. Okay, and penstock is the main important part of the penstock formula. Is basically we have to find the thickness of the penstock pipe. I think there is some formula error, but I will do this. I have to check this because I did not. Anyway, this is so basically the thickness of the pipe is because that is the cost. No, it's one thing is the material used is mild steel or high density polyethylene pipe, rigid unplasticized PVC, and they call it UPVC. So you can use these type of materials, but normal common material is mild steel. So depending on the thickness of the pipe, cost of the penstock will depend on the thickness. So basically, we have to calculate the thickness of the pipe, and this thickness of the pipe depends on the internal pressure, internal radius of the pipe, the allowable stress. In this is based on the material use. The I think here it should be the welding joint efficiency should be the question mark is the joint efficiency, and epsilon is the corrosion allowance. So you allow 2 millimeter of corrosion, the pipes can corrode. So this is how you calculate the penstock, and the main cost will be based on the thickness, the weight of the penstock. So, but another factor you have to consider is you have to consider the head loss. Okay, again, like we did in the tunnel, the head loss in the pipe is important. And when you do the head loss in the pipe, the velocity is based on this one. And the total head loss is wall loss plus turbulent loss, losses due to friction of the penstock walls and the turbulence. And the formula used is the wall loss formula is based on Darcy, what's known as Darcy-Weisbach equation, and the F value is friction factor for pipes. Is you can get it from what is known as the Moody diagram. The friction fraction based on the Reynolds to find this thing. I will not go into the detail now. I just wanted to mention that we need to find the losses in the walls and the turbulence loss, which is due to in the entrance when there's a bend of the penstock, when there's a contraction, where there's a valve, there is a loss also. The total loss will be the head loss coefficient thing, and the friction F is you get it from the friction factor. So based on the loss, like we did for the pan, we also do what is known as the penstock optimization. So what you do is, once the diameter increases of the penstock, the cost increases. When the diameter increases, the head loss decreases. So when the head loss decreases, this loss of energy decreases. So you find the total cost, which is equal to cost minus the energy lost, and whatever cost comes out to be total cost out to be the minimum. We call this the optimum diameter, like we did for the tunnel earlier. Like this equation for a typical tunnel optimization for the penstock, also we use this diagram. So this is how a penstock optimization is done. And apart from that, for the penstock, you need to, you need to also have anchor blocks. You need to have support piers to support the penstock using so that when the penstock, when the water flows and there is reversible flow in the penstock, these penstocks are still stable. So it does not move or it doesn't break. So these support piers and anchor blocks are also part of the hydropower civil works design. Okay, I think I will now stop here for questions. So sorry I went a little fast now because I wanted to cover, this was something that I planned to cover yesterday, which I could not do. Carlos, any questions here before we take a break?
Thank you, Divas. Let me just check. Alguma pergunta, colegas, antes do intervalo? Alguma pergunta? Queiram colocar uma dúvida? Yeah?
question related to tunnels. Just to understand, is it common in cities to use the tunnels to generate energy from the sanitation water, the city sanitation water? Is it common?
Uh, if I to use tunnel to, what was the second part of the question? Can you repeat your question, please?
To use the water sanitation from city water sanitation to generate energy through tunnels. Normally, the city sanitation is done by tunnels. Is it common to use this water to generate energy?
Uh, no, actually, we have to be careful using city water supply, because you have to have, I don't know if these tunnels are pressure tunnels, okay? Because the main thing is, if it is, if like, I think I have it here. I don't know, let me see if I go to my, let me just, okay. Yeah, you can see my layout, okay? Yeah. So basically, uh, for a tunnel, you have to be a little careful. Is because you need the head. You see, now for a tunnel, headrest tunnel over here, the water is from this reservoir. Okay, so the water that is flowing in this tunnel is under pressure. Okay, so basically, when I say it is under pressure, it is basically the water is flowing full. So it's like a pipe flow. So if the city water supply has that sort of a facility, but I doubt if that will be possible for a city water supply. It has to check that, because it has to be under pressure, and I'm not sure. Of course, supply is under pressure, but that pressure is to supply water to different consumers. So I'm not sure if it is possible. I doubt if it would be possible.